So I'm Nakul, and together with Tobias, today we would like to talk to you about how we do monitoring of distributed systems at Trademob. Just to give you a bit of context, Trademob is a Berlin-based startup, and we are a mobile app marketing platform. We do things like user acquisition, retargeting, and we're also a mobile-only demand-side platform for in the real-time bidding ecosystem. So I think a lot of people already heard about RTB systems a bit earlier in one of the other talks. This talk is going to be a two-part talk. The first part, I will talk about how the architecture and the engineering part of how we monitor at Trademob, while Toby will then talk about the science and the techniques behind how we do these things. As a DSP, we are used to handling about nearly from 10,000 requests a second to 100 or 150,000 requests per second on a daily basis. So this naturally means that the infrastructure costs that we have at Trademob are fairly high. So our infrastructure has to actually scale organically based on our traffic. As Etsy already popularized measure anything and measure everything, no matter what scale you are, I think collecting metrics gives you visibility into what you're actually doing, helps you increase your mean time to detect or respond to the issues that you're facing in production. But at the scale that we are operating in, it quickly became an issue for us. We were collecting about 2,000 metrics per second, or on average, and around 5,000 individual metrics per second at peak. The number of dashboards to developers that we had was too much for us to deal with. So when you can't really gain insights from your metrics you're collecting, you no longer have control over the services that you're building. We needed something a lot more smarter. At this point of time, a trending topic that was in the community of monitoring, again, as popularized by Etsy and Twitter, was anomaly detection. So we thought, OK, now we have all this data, and we can apply anomaly detection or outlier analysis on top of this data to actually gain insights to when things go wrong. But we quickly realized that the number of false positives that we actually got with anomaly detection was way too much. The number of alerts we were getting were insane. Our email was being bombarded by false positives all the time. Clearly, this wasn't helping us. So, of course, what this meant was anomaly detection was an extension to your toolkit, and it was not just the solution itself. We need to apply something additional to anomaly detection, techniques such as convergent cross-mapping or seasonality or trend decomposition to actually combine the signals from multiple algorithms and then collectively make decisions based on this. But unfortunately, there wasn't a system or a project that let us do this fairly easily. So we decided we wanted to build something on our own. And we had a set of requirements for that. It had to be real time, or at least near real time. I have to apologize because the talk said real-time monitoring of distributed systems, but this is not possible because of various aggregation or policies that you have in terms of how you're collecting the metrics themselves. Now, also we wanted an isolated point of view from different algorithms or techniques based on the metrics that we were collecting. We wanted anomaly detection or seasonality to look at the same data points at different perspectives in an isolated manner so that we could gain the signals from these and then use them. Naturally, the reason for us to actually build this, so that was for us to optimize our infrastructure costs. So the system had to have a really low footprint in terms of maintenance and operation costs. And finally, it had to be extensible. Extensible in terms of adding new algorithms or new techniques, and also the data sources that we were actually integrating with. So we wanted to be able to even measure and collect metrics from the dashboards or our business KPIs or others. And this actually led us to build Anomaly, as we call it. Anomaly is a Python project that lets you collect metrics and then analyze these with multiple techniques with dynamic, which allows you to have dynamic monitoring at the end of the day. The main focus here for us was to abstract the complexity for developers so that you could just plug in your metrics and then have multiple algorithms looking at this. Now, before we actually did this, we had to deal with another issue. We had to scope the metrics. We are talking about distributed systems here, which means that we have a large number of instances running across in different groups or different clusters. And all of these instances or services are actually sending two kinds of metrics. One is application metrics, which come from your services, and the second being the system metrics, such as CPU or disk or whatever. Now, what do I mean by scoping? We wanted to look at these metrics not just at an individual or an instance level, but at different levels of granularity. We wanted to have a micro and a macro view on the services and the metrics that we were collecting in terms of an instance level or a cluster or any sort of logical grouping at different levels. So we needed to build a solution for this, which meant that we had to hack certain parts. To give you a small example, this is one of a metric that comes from one of our services. As you can see, it has a number of different tags, including the host name, the region, or the auto-scaling group, or the availability zone, and so on. Now, when such a metric is pushed by the service, we then multiplex it. By multiplexing it, what we get is a number of possible combinations of that individual metric based on the tag. So one metric, when we actually receive an anomaly, it becomes multiple that is split at different levels of granularity. These are then aggregated based on different policies with different interval periods, so that when the data is actually received at anomaly, it's ready for the algorithms to dig in and start doing their magic. To give a short overview of the architecture itself again, this is what anomaly looks like. We have a number of services sending metrics to our multiplexer or aggregator layer, where each metric is multiplexed, aggregated, and computed, and then it is pushed to the collector layer. The collector layer is a Python implementation on top of libuv that performs really well, and it pushes data to what we call a metric store, which in our case happens to be Redis for sake of simplicity. But you could easily plug in any other key value store based on your scenario. Now, once the metrics are in the metric store, we have the task runner, which is basically a Celery instance that is running behind the scenes and selectively runs different algorithms on the data in the metric store. And then this triggers further data or events, which are then handled by event handlers. Now, in our case, these event handlers could be something as simple as sending out an alert, or it could also be something like killing an instance because it is performing suboptimally. So, Anomaly, to summarize the architecture, it's just lets you selectively collect metrics and then analyze this and trigger events upon which you can then react to, leading developers to have a hands-free approach on top of this. Now, Toby will talk about the algorithms which we actually use to have in production.
Yeah, thanks, Nakul. As said, I will going to present the algorithmic part of Anomaly. And first of all, I would like to start with a short introduction how anomalies could look like in our case and what possible ways there are to solve those issues or to detect those issues. So the first example is rather simple. It's just showing the CPU utilization of a single box, which suddenly peaks at 100%. And of course, it's also quite easy to detect. If we just apply a static threshold, we can catch this and react on that. The second example also shows CPU utilization. In this case, it looks rather okay, so it's quite stable over time, but it is not okay if we put this into context. This means the green band, what we see here, we'll come to this in a bit more detail in the next slides, defines something like an expected state of this box in this particular service. And yeah, the shown box obviously does not fit into that. So depending on the time, you can define this also as an outlier. And the third example is a time series plot of incoming system requests at Trademob. We see 3 consecutive days, and I guess you all see also the outages, what we have here. And well, the problem here is more of having an algorithm which is capable of detecting outages like this. And if we all put this together, it leads to the point that before we can do proper anomaly detection, we need an idea of what we expect from our system. So we need a definition of normality before we can judge certain situations as okay or as falsy in the end. And in the following, I would like to go into two different directions. The first one is the behavior of the distributed system. So as mentioned, we are running up to 1,000 boxes at a time. And yeah, the question is, how do single boxes within specific services do behave? And the approach we are using is rather simple. It's the so-called Tukey's outlier filter. And yeah, in the end, it's using statistics. So what we see here is a distribution of different instances of, again, CPU utilization. I don't know if you see it. It's from 0 to 100%, and we see the most of the boxes are at around 50 to 60, 65%, but there are also some which are far below or above those values. And yeah, the question is, how can we judge or how can we get them as outliers? And one way of doing this is applying quantiles to that. So what we see here is the quantile 25 and the quantile 75. So quick reminder, quantile 25 is just a cutoff from the lower 25% to the upper 75% of the distribution. And both values together define the so-called interquartile range, which is a quite robust statistics containing the middle 50% of the values. And if we now take a constant of that and add it to the quantile 75 and subtract it from the quantile 25, we get this green band, which yeah, in the end defines something like a healthy range or a stage of the system which we accept, and everything above or below we would then define as an outlier. This is only a snapshot. If we look at it over time, it looks, of course, more like this. So we have, again, the evolving green band, and most of the instances are okay, but there is one box which is only using a fraction of possible CPU. And yeah, you can say we are essentially losing money there because we are not using what we could use. So if this states persist for a fixed period of time, like 1 hour or 2 hours, we can react on that by just restarting the service or kill the box in this case. To sum this up, the idea here is that we want to identify auto-scaling issues, not only about CPU, you can also think about memory leaks or business values also, so incoming requests per box, for instance. Of course, the approach has restrictions, so in the end what we always need is kind of a healthy range. So if you think about a service group and all boxes have issues, you would still define something like an interquartile range, and you would define a lot of boxes as healthy, even though the whole service has problems. And to tackle this, it's not sufficient to just use this, of course. So we also need to look at the overall system performance. And yeah, one last word to CPU usage. You can just think about taking the average CPU usage of all the boxes within that service, and if this metric has issues, then, well, the whole service has issues and not only a couple of boxes. And yeah, also here there are several ways to go on this problem. The approach what we are using is mostly the so-called seasonal trend decomposition algorithm. It's using the fact that most of our metrics have this inherent seasonality, which is 1 day usually. So what we see here are 7 consecutive days, and yeah, I guess the pattern is quite obvious that those are daily metrics, and by the use of this, you can then apply this algorithm and decompose this time series into 2 parts. So we have first the seasonal part, which is then more or less identical over the days. And we also have the trend part. It's also looking quite constant. In the end, we see a slight increase, and that is for a good reason. So if you look into the days, you see that this was Saturday, Sunday, and we have a slight increase of traffic. And yeah, this is reflected by this trend component. How do we use that? Another example to that, so incoming request for 2 days again. And we now apply the algorithm and decompose this time series. and generate those two time series, seasonal and trend part. And you can just add them up now. So you can create a model of your incoming service metric. So that defines something like the expected state. And if you put this together to the raw input and just take the difference, it's quite obvious that you get the distribution of error or deviation. And in this case, with simple thresholds, you could detect those outages. Unfortunately, it doesn't look that nice all the time. So this final error distribution in reality looks more like this. So we have peaks, drops, longer ones, stronger ones. And the question is, of course, when do we want to react? So the overall goal is for sure that we have a very small number of false positive, but we want also to detect as much as issues we have. So there are several ways, and this is actually a big part of the whole problem, how to judge those distributions. Just to name a few, you can use normalization, for instance. If you have a broad range of your incoming metric, you can set minimum deviations. You can use static thresholds. And the way we are going for usually are dynamic thresholds by the use of T-digest, which was, I guess, some of you heard it yesterday, presented by Ted Dunning also. So quite nice online clustering to estimate quantiles of your distribution. And if you apply this or a combination of that, then essentially we want to build something like that. So we have a flag now which is just saying everything is fine or we are in an error state. And depending on the length of this error state, we then can take actions like restarting services or boxes or alert some responsible persons for sure. That's it about Anomaly. Last but not least, we decided that we want to open source this project. So actually it's already open sourced since today. So you will find that on GitHub, the whole Anomaly project, and additionally also a Python implementation of T-digest, which is heavily used within Anomaly. And well, that's it from my side. Thank you very much.